Welcome to Kactus2. In this video, we explore the IP-XACT standard in Kactus2. The original idea for IP-XACT was launched in DAC 2003 conference as a need for IP reuse. The idea formed into a standard by 2009, the 1685-2009, and was first maintained by the Spirit Consortium, and later the Accelera Initiative. The standard has been updated twice, first into the 1685-2014 version, which itself was superseded by the 1685-2022 revision. IP-XACT is a structure for packaging, integrating, and reusing intellectual properties, or IPs. It is an industry standard for design data exchange, containing nearly 1,000 properties for defining IP documents using an extensible markup language, or XML format. Kactus2 is designed to create and modify these IP-XACT documents. IP-XACT uses different types of documents to identify and contain distinct data sets. The core documents of IP-XACT that have been implemented in Kactus2 are component, design, design configuration, bus definition, abstraction definition, and catalog. All top-level documents are identified by a unique identifier, VLNV, vendor, library, name, version. Cross-references made to documents are done using the VLNV. For example, tuni.fi, peripheral.components, UART, 1.0. Tuni.fi is the vendor, peripheral.components is the library, UART is the name, and 1.0 is the version of the document. An IP-XACT component is a static, structural model of a single IP, such as a processor, UART, or a crossbar. It can be considered equivalent to a VHDL entity or a Verilog module. IP-XACT components are reusable through their configurable parameters, parameterization of elements, and multiple implementations, with the same external interface. HDL ports can be translated into IP-XACT physical ports, with each port describing a single external port of the containing component. Ports can be connected to other component ports through ad hoc connections in the design document, or combined into groups using bus interfaces. Bus interfaces are primarily defined by two definitions: the bus definition, which specifies the used protocol, and the abstraction definition, which defines the logical signals on the bus. These logical signals are mapped to the physical ports of a component through the use of bus interface port maps. Wire ports are connected to wire signals, and transactionals to transactionals. The purpose of a bus interface is designated by its interface mode. There are 7 different modes, 3 for standard functional interfaces, their mirrored counterparts, and a monitor interface. Mirrored interfaces reverse the port directions for port mapping. Initiator mode is for initiating transactions. It can be assigned a specified base address, as well as an address space to describe the range of available addresses for transaction generation. Target mode responds to transactions. It can contain a reference to a memory map, defining the range of registers accessible through this interface, or the interface can be used to create a bridge to a selected initiator interface. System mode is used for classes of interface bus types that do not fit initiator or target category, and they must contain information about their system group. Mirrored system mode is a mirrored version of system mode. Mirrored initiator cannot be assigned a base address value or an address space, but is in any other way a mirrored version of an initiator interface. Mirrored target mode is a mirrored version of the target mode without the connected memory map, but with additional address offset and range values to the connected target interface. Monitor interfaces are purely for non-intrusive observation of interconnections. IP-XACT has a hierarchical memory model contained within component documents. Its base block is the memory map, which is accessible through a target bus interface. Memory maps may contain address blocks, memory banks, or subspace maps, and can also define an address unit bits value. If an address unit bits value is not defined, it is presumed to be 8. Address unit bits defines the number of data bits each address increment contains. For example, If address unit bits is 32, a 32-bit register would require a single address, 0. If address unit bits is 16, the same register requires two addresses, 0 and 1. If address unit bits is 8, the register uses four addresses, 0, 1, 2, and 3. Address blocks are a continuous block of memory, reserved area, registers or register files. Registers define the software interface, while fields describe the register bits. Register files are groups of registers and register files. IP-XACT defines an address space as a logical addressable space of memory. It can be assigned to an initiator bus interface, in which case it can be seen as a programmer's view out of the bus interface. Address spaces can be divided into segments with defined address ranges. Each address space can also have a local memory map, an area of memory visible only in the containing address space. A view defines the representation of a component, such as RTL, TLM, simulation or synthesis. This representation is done through the use of instantiations, component, design and design configuration. Component instantiation defines the component. It contains the specific implementation details, such as the relevant files, language, library, and package and language-specific module parameters. Design instantiation is used to define a design document for use with the containing view. Design configuration instantiation is the configuration document that should be used with the design, either referenced by the design configuration, or used in the design instantiation of the containing view. An IP-XACT design is a collection of component objects metadata, component instances, connected with interconnections. A design can be viewed as a model of a system on chip. A component with a view element that defines a design instantiation is considered to contain a design. This is called a top-level component in Kactus2. This allows the component to influence the design using its parameters, bus interfaces and ports, while the design itself can be transferred to another component. A component instance is the instanced representation of a component. All of its enabled physical ports and bus interfaces are connectable to other component instances, or the top-level component using interconnections. If a component instance is configured to use a view containing a design, the instance is considered to be hierarchical. This means that there is another design connected to the component instance. There is no constraint on the depth of this hierarchy, and pre-existing component instances can be used on multiple levels, though circular references are not allowed. Component instance parameters can be modified to design-specific values using configurable element values. This allows the parameters to travel from the top-level component through the design to a specific component instance. To enable configurable element value editing for a parameter, its resolve value must not be immediate. For example, if we want to change this component instance's parameter value to the top-level component's parameter, we will first need a design parameter. The design parameter is then inserted as a configurable element value for the desired component instance, so that through this design the component instance has the selected value. Then we can change the design instantiation configurable element value in the top-level component to use the selected top-level component parameter. When the design is viewed through the top-level component, the parameter of the top-level component is transferred to the component instance. Interconnections connect the component instances through bus interfaces. This way the ports mapped in the bus interfaces are connected. In order to connect bus interfaces, they must use the same bus definition and have compatible modes. Interconnections are similar for both RTL and TLM models. An RTL signal is called a wire, while a TLM signal is called a transactional, and RTL-TLM crossover is done with abstractors. For connecting individual ports, ad hoc connections are used. An IP-XACT design configuration contains additional configuration options for a design. Design configurations are linked to a single design, but a design can have multiple design configurations. Design configuration contains the view selection for each component instance. The instantiations of the view are activated when the view is selected, allowing the component instance to be modified for different purposes. The base for address definition is the address unit bits. It defines the number of data bits in each increment in address. In IP-XACT, the default value for address unit bits is a byte, or 8 bits. The required memory space of the address is defined using the range and width values. Range defines the memory space as the number of address unit bits, while width specifies the row width, depicting the maximum single transfer size by a bus interface. The total number of bits a memory item takes is address unit bits times range. IP-XACT design structure allows mapping of address spaces to registers. Registers are physically located in the components. Each register has a base address and range determining the memory area of the register. This can be tuned using bus components to introduce address transitions. Bus components are IP-XACT components that have either a bridge, transparent or opaque, or a channel for internal connections. Channels are a separate element of a component document that defines a connection between a mirrored initiator and a mirrored target. It can be either a single association, or multiple combinations of the two bus interface modes. The mirrored target allows address transition through address remap and range elements, defining a new address for the connected element, as well as reimagining the range of the connection. Transparent bridges are associated with target bus interfaces. It internally connects the selected initiator bus interfaces to the target. The initiator bus interfaces can then modify the base address of the connection. Opaque bridges are internal connections made through the use of memory map subspace maps. A subspace map connects to a segment of an address space, which can be assigned to an initiator bus interface. If the memory map containing the subspace map is connected to a target bus interface, it creates an internal connection between the subspace map and the segment. Final mapping of the register is resolved by traversing from the address space to the connected memory maps, following all the address transitions made by the connected components in the bus interfaces along the route. Vendor extensions are vendor-specific data related to an IP-XACT element, such as positions of component instances in a hardware design. Vendor extensions are not cross-compatible between tools, potentially causing vendor lock-in. Kactus2 minimizes the use of vendor extensions for these purposes, though it does have an editor for user-defined vendor extensions for applicable elements. The IP-XACT standard is a complex, but versatile structure. Proper use of it can help in maintaining and reuse of an IP library. Thank you for watching this video. For more information on Kactus2, please see the other tutorials, or visit our GitHub page.